On Friday, we took a look at a little experiment that enabled us to find the threshold frequency of a particular metal. Among other things, the threshold frequency of a particular metal. Here's our metal right here. Whatever it is, we have photons that strike that metal and cause the electrons to be ejected. In other words, those photons must be above the threshold frequency of that metal, whatever it is. Those electrons will leave that metal with a certain amount of kinetic energy, and they're going to start going over here. Now, with the way that we have this set up right now, a positive end of the power supply right here causing a positive collector, and a negative side of a power supply right here, these electrons that have been ejected will be attracted to this positive collector. They will speed up as if it's a car going down a hill. They'll speed up towards that collector. As they do that, and as they enter this collector, they're going to start going around this circuit right here. That's what we call an electric current. Electrons moving through a wire is an electric current. Because we have an electric current, this ammeter, which measures electric current, will measure a value that's not zero. In other words, we'll get a current here that's 2 amps or whatever. Now let's switch around this power supply. Let's swap it around so that this power supply is set up like this. Negative end of the power supply, positive end of the power supply. That makes this collector a negative plate. And it makes this one over here a positive plate. Now these electrons are still going to be ejected from the surface as long as these photons are still above the threshold frequency. But this time, as they're ejected and moving towards the left, they're going to be slowed down by this potential difference. It's like this time they're going up the hill instead of down the hill. If I apply a big enough potential difference by this battery right here, then I can stop these electrons dead in their tracks. How do I know when they're stopped, though? I can't see physically with my eyes these electrons, so I can't tell just by looking at them when these electrons have stopped. Here's what's going to happen. If my potential difference is small, then I'm going to get a current going around here. And I'm going to measure that current with the ammeter here. Let's say it's 1.0 amps. If I apply a big enough potential difference, then I'm going to stop those electrons dead in their tracks. That's going to give me a current reading down here of 0. When I read 0 amps on the ammeter, I know that I've stopped the electrons. I know that the potential difference that I applied across this battery is the stopping potential. I record that value. In fact, I record the value of the frequency of the photons and the stopping voltage or the stopping potential that caused those electrons to stop. And then I repeat the experiment. I put a new frequency of photons, a new stopping potential, a new frequency of photons, a new stopping potential, a new frequency of photons, a new stopping potential, and so on. Then I create a little analysis table. Frequency is still the same, but my second column will now be kinetic energy of the electrons. How do I get kinetic energy from the stopping potential? You guys know this, right? Equations on your data sheet. EK max is equal to Q times V stop. So let's take each of my values for stopping potential, get kinetic energy. Let's compare that against frequency by plotting a graph. It's going to look like this. Frequency is on my x-axis, my manipulated variable. Maximum kinetic energy of the electrons on my y-axis, my responding variable. The graph will be a straight line, but it'll be a straight line that goes through the x-axis. Tell me, please, what equation describes this straight line, or any other straight line for that matter? Y is equal to mx plus b. We've seen that a million times before. Okay, we'll see it a bunch of times between now and the end of June. Y equals mx plus b. On my y-axis, I have what variable? Ek. So let's sub in Ek for y. M is the slope. And on my x-axis, I have frequency. I can't scratch off the y-intercept this time. We talked about this on Friday. It looks like there's no y-intercept here, but there is one. There is one because it goes to the x-axis. It's going to ultimately go through the y-axis as well. If we extend this back, extrapolate this back here, the y-intercept is a negative value, but it's still a y-intercept. We can't get rid of the b because there is a y-intercept. Now let's find an equation on our data sheet that has the same variables as the equation from the graph, EK and F. Anybody tell me what equation that is? I'll give you a hint. It's not actually on your data sheet. Usually they are. This one's not. This one we have to come up with ourselves. HF. Remember this one? HF is equal to EK max plus the work function. Let's rearrange it now to take the same form. EK ends up being equal to HF minus W. So solve for EK because the equation from the graph solves for EK. Let's scratch off things that appear in both. EK is in both equations. F is in both equations. We're left with the slope in this equation is equal to Planck's constant. And we're left with B, the y-intercept, is equal to negative W, the negative of the work function. How do you think we found the value of Planck's constant? How do you think we know it's 6.63 times 10 to the minus 34? Well, we know it because a graph of EK versus F gives us a slope of 6.63 times 10 to the minus 34. That's how we know it. How do you think we know the work function of a particular metal? We plot a graph of EK versus F for that metal, take the y-intercept. That gives us the work function. Now, there is one more way to find the work function, by the way. Every once in a while, you get a graph that's difficult to determine the y-intercept. You want to extend this back, but maybe you run out of paper. You can't extend it back far enough. Maybe there's no numbers along the y-axis below the x-axis. So you can't find the y-intercept in a practical way. We know that the work function is also equal to h times the threshold frequency. H is the slope. So if we take the value of the slope, that's half the battle there. F0, the threshold frequency, is the x-intercept. That's the frequency at which electrons begin to have kinetic energy, the frequency at which electrons begin to be ejected. So we can find the x-intercept by taking, we can find the threshold frequency by taking the x-intercept. We can find the Planck's constant by taking the slope. We can find the work function by taking the absolute value of the y-intercept. Or we can find the work function by multiplying the slope times the x-intercept. Does that make sense? Okay, second time through this, but we had a few multiple choice questions that I asked you to work on as well. 115, and then we also had 119 to 122 that I mentioned on Friday that I'd like you to do. I'd like to go over all four of these questions here. How many people for 115, for question 115, said A? B? C? D? Okay, of those people that volunteered an answer, we got C here. Let's take a peek at it. What's the maximum kinetic energy of the emitted photoelectrons? Here we've got a frequency. Here we've got a stopping potential. We want to find the kinetic energy. The easiest way to do that is to say EK is equal to QV stop. Kinetic energy is also equal to 1 FmV squared, but we don't know what the speed is, so let's just use the QV stop equation. We multiply those two numbers together. We do, in fact, end up getting C, 2.00 times 10 to the 19. What value for Q do we use here? We're not told what the value of Q is. So how do we know what its value is? What is it that's ejected here? Electrons. So what are we going to use? The charge of an electron, 1.6 times 10 to the minus 19. 119 says the threshold frequency of light for the emission of photoelectrons from a metal is 4.4 times 10 to the 14. The frequency of light is 6.6 times 10 to the 14. So in other words, we're shining light on this metal, light that has a higher frequency than the threshold frequency. In other words, electrons will be ejected. We want to find the max kinetic energy of those electrons that are ejected. Let's try the equation HF is equal to EK max plus W. H we have, F we have. Be careful not to get those two F's mixed up, by the way. EK we're looking for. W we don't have, but we can sub in an expression for that. EK plus H times the threshold frequency. So we've got this, got this, and this. Take this over by subtracting. And we end up getting EK for number 119 equal to D, 1.5 times 10 to the minus 19. Oftentimes when we get a question like this, we can look at our options and say, oh, okay, I know this one and this one have to be wrong, just because of the numbers. Here we can't. Here they're all 10 to the minus 19. And generally, when you're looking for kinetic energy of an electron ejected from the photoelectric effect, it will be somewhere in that 10 to the minus 19 range. You get 10 to the positive 32, you're wrong. If that's one of the options, then don't bother picking it, because you know you're wrong. Is there a question back there, Michael? You good? Okay, H is that Planck's constant, 6.63 times 10 to the minus 34, or 4.14 times 10 to the minus 15. We could have used either one there, although odds are if we're looking for kinetic energy in joules, we're probably going to use the 6.63 value. Okay, this next one involves, in fact, the next three questions involve this information that appears. It says, on a movie film, the soundtrack is located along the side of the film and consists of light and dark regions. Light from the projector is directed through the soundtrack and onto a phototube. Variations in the transparency of the regions of the soundtrack allow varying intensities of light to reach the phototube. So you can look at this and say, all right, in region 3, that's the most transparent part. So region 3 is the part that's going to allow the most intense light to go through. Region 2 is the least transparent part. It's the darkest spot, so it's going to allow the least amount of light to go through. Before we even look at the questions here, let's just think about what's going on here, okay? Light goes through here. It strikes a phototube. What does that do? If light is above the threshold frequency and strikes a photoelectric surface, what does it do? What happens? Electrons are ejected, right? Electrons are ejected. That provides us with an electric current, these ejected electrons. If you have one photon above the threshold frequency, then you get one electron. If you have 50 photons above the threshold frequency, you'll get 50 electrons. In other words, more photons, more electrons, if you're above the threshold frequency. These are all above the threshold frequency. More transparent, in other words, region 3, allows more photons to go through, therefore will eject more electrons, therefore will cause more electric current. Region 2, less photons through, less electrons ejected, less electric current. Let's see what we're being asked for in the question here. The region of the soundtrack that will allow the most electrical current to be produced in the phototube is labeled what? The most electric current is going to come from the most photons going through, which is region 3, option C. 121, the work that's required to move the electron from the photoelectric surface in the phototube is called the, somebody in my period 2 class said the threshold frequency. The answer is the work function. B is real close, though. How could we change this question to make B the correct answer? One word. Let's change the stem of the question by one word to make B the correct answer, not A. Which word would it change? Yeah. We're going to change energy to frequency. The frequency that's required to move the electron is the threshold frequency. The energy required is the work function. Finally, 122, a bit of a tougher question here. This one says, in 1 second, this many photons are incident on the phototube. If each of the photons has a frequency greater than the threshold frequency, then what's the current? The only equation that we have for electric current is from our last unit, Q over T. The time here, if you read between the lines, is 1.0 seconds. We're told in 1 second, this many photons. If you have this many photons, how many electrons do you have ejected? If you're above the threshold frequency, 1 photon causes 1 electron. 50 photons causes 50 electrons, Michael? Same amount. 1.45 times 10 to the 16 photons. But we don't want the number of electrons here to plug in for Q. We want the charge of those electrons. So let's take the number of electrons that we get, 1.45 times 10 to the 16, and multiply that by the charge of 1 electron. That gives us a value for charge of 2.32 times 10 to the negative 3. Let's plug that value in now. And we end up getting 2.32 times 10 to the negative 3 amps. So the amount of charge that's produced here is 2.32 times 10 to the minus 3. But because that charge is falling in 1 second, then that's the current as well. How do we express that? A decimal BC times 10 to the D? 2323. We drop the decimal point there. In 1887, Ina Kurtz discovered the photoelectric effect. Light strikes a piece of metal. Sometimes an electron is ejected. In 1905, 18 years later, Albert Einstein explains the photoelectric effect, why it works the way that it does. He explained it by saying that light exists as a particle of light called a photon. A photon is a quantum of energy. The energy of that photon, the energy of that particle of light is equal to h times f. It's related to the frequency, not related to the amount of light that we have, but rather the type of light that we have. Fast forward a few years, 1923, Arthur Compton observes that if you take a photon that's really, really, really high frequency, really, really high energy, in other words, something like an X-ray, and you shine it upon this piece of metal, then yeah, you'll get this electron that's ejected, but sometimes you'll get a second photon ejected as well. Not just the electron coming out of it, but rather an electron and a photon coming out of it. Now, classical theory, old-style physics, would predict that that second photon is really just the first photon. It's just bouncing off. Okay, a photon strikes a piece of metal, an electron, for whatever reason, is ejected, and the photon bounces off. But Compton observed that that second photon was less energetic than the first one. In other words, if it had less energy, it had less frequency, according to Einstein's photon theory. In other words, it's a different color. Instead of having really, really high frequency X-rays, as we have in the incident ray, we have lower frequency X-rays. Instead of having low frequency X-rays, as we do in the incident frequency, maybe we have high frequency ultraviolet bouncing off of it. Well, how do we explain that? How do we explain the fact that, there's electrons ejected? We kind of already explained that with the photoelectric effect, right? But how do we explain the idea that the photon that comes off it isn't the same photon that hit it? It's like saying you got a collision of cars. Two cars collide. Okay, you got let's say a Ford Mustang, and it collides with a Chevy Camaro. Well, the Camaro bounces off this way, and all of a sudden, what was the Ford Mustang is now a Ford Festiva. It's changed. It's a different car now. It's a lower energy car, a lower frequency car. How does that happen? It doesn't make any sense. How is that second photon going to be a different frequency and therefore a different energy than the first photon was? Well, Arthur Compton reasoned that it is just like that collision of cars. Whenever we have a collision between two cars, or whenever we have a collision between a photon and an electron, it's really just a conservation of momentum problem. In other words, the momentum of the original photon, okay, some of it gets transferred to the electron as the electron gets ejected. But that that photon that gets scattered, that second photon, must have less momentum than the first one did. Just like when the Mustang hit the Camaro took some of its momentum, the Mustang is going to have less momentum. The difference here is this. When the Mustang loses momentum, it doesn't change the type of car that it is. When a photon loses momentum and loses energy, it changes the type of photon that it is. So Compton argued that it is a collision between a photon and an electron, and therefore the photon is going to lose momentum and lose energy, and therefore it's going to change from one type to another. That seems logical, seems reasonable. But that created its own problem. What's the equation for momentum? Very first equation we learned this year. What's the equation for momentum? P equals m times v. What's the mass of a photon? 0. Not very little, 0. If the mass of a photon is 0, how can that original photon have momentum? How can it give momentum to the electron that was ejected? And how can the second photon be less energetic or more energetic or anything if photons just don't have momentum? How can we analyze this as a collision in which conservation of momentum applies if photons, which is the biggest part of this whole thing, don't have any momentum? Well, Compton argued that they actually do. You're going to see in a minute, after you write down a few lines of notes here, where that argument comes from, where the idea that photons have momentum, despite the fact that they don't have any mass, where it comes from. Get you to copy this out here first. Next couple minutes. And then we'll break the surprise for you. I know everyone's just desperate to find out how photons can have momentum when they don't have any mass, but you're going to have to wait a couple minutes. Now is the moment you've been waiting for the last 3 or 4 minutes. Now we can find out exactly how a photon can have momentum when it doesn't have any mass. The equation that describes its momentum is, of course, P is equal to m times v. Again, that first equation that we learned in all of Physics 30. Enter Einstein again. Second time in a couple of days here. Einstein said that energy and mass are not the same thing, but they're two different forms of the same thing. It's kind of like saying steam and ice. Steam and ice are two different things, but they're two different forms of the same thing. They're both H2O. Liquid water, for that matter, is another form of the same thing. We can convert steam to ice and to liquid water, and we can convert liquid water to steam or to ice. We can change those things back and forth. If you have a certain amount of ice, it's not steam, but it's like having a certain amount of steam. If you have this much liquid water, it's like having this much ice or this much steam. Mass and energy, Einstein said, are kind of similar to that. Einstein said that these two things are two forms of the same thing. Therefore, if we have a certain amount of energy, it's like we have a certain amount of mass. And if we have a certain amount of mass, it's like we have a certain amount of energy. They're interchangeable pretty much with each other. Because of that, we don't need mass for a photon to have momentum. We can have energy because energy is like having mass. Now, we need to be able to quantify that, though. Enter probably the most famous equation ever in physics, maybe the least understood equation ever in physics. What is it, Michael? E equals mc squared. Einstein said that if you've got a certain amount of mass, let's say a kilogram of mass, and you multiply it by the speed of light squared, you're going to get a certain value of energy. That would be 9 times 10 to the 16 in this case. In other words, 1 kilogram of mass, if it could be converted completely to energy, would be the same thing as saying 9 times 10 to the 16 joules of energy. It's a whole lot, right? A little bit of mass makes a lot of energy if you can convert it 100% efficiently. Well, Compton used that equation that Einstein had already come up with and said, I don't want to find the equivalent energy. I don't want to find out how much energy a certain amount of mass is worth. I want to find out how much mass a certain amount of energy is worth. So I'm going to take that equation of Einstein's and rearrange it. M is equal to E over C squared. And then he said, I'm going to sub in that expression right here. So my momentum becomes not mass times velocity, but rather it becomes equivalent mass times velocity. Instead of saying, you know, we got this much steam, we get this much ice, which is worth the same as this much steam. It's the same thing as having this much steam. Okay, instead of saying we have m, well, I'm saying we have E over C squared, which is the same thing as having m, having the mass. So it's the equivalent mass times the speed. I'm going to cross off a v in a 2, though. Why can't I do that? If that was a c over c squared, then we could cross off a c easily, right? But we get a v over c squared. What's the deal with that? How come I can cancel something out there? Right. What's the value of c? 3 times 10 to the 8, right? What's the value of the speed there, v? 3 times 10 to the 8. So v and c are the same thing here. It means we can cross them off. We're left with this. P is equal to E over c. The momentum of a photon is equal to the energy of a photon divided by the speed of light. Now all of this stuff seems to work. The whole Compton scattering thing where we have an electron emitted, a second less energetic photon emitted that would require photons to have momentum. Now we can say that that seems to work. The observations seem to fit with this theory because now we understand that photons can, in fact, have momentum. We can treat it as a collision because photons can have momentum. It's just not equal to m times e. It's equal to E over c. On your data sheet, it actually appears this way. E is equal to P times c. So instead of solving for momentum, on your data sheet, we solve for energy. The energy of the photon is momentum times the speed of light. Now, we can sub in HF for the energy as well, because we know that E is equal to HF. That equation doesn't appear on our data sheet. We can also sub in HC over lambda for the energy. So it becomes HC over lambda over C, which, of course, the C's cancel. We're left with P is equal to H over lambda. That one does also appear on your data sheet. If you look in the top right-hand corner, you're going to see E equals mc squared. You're also going to see E is equal to P times C. You're also going to see P is equal to H over lambda. If you're asked to find the momentum of a car, let's use P equals mv. If you're asked to find the momentum of a baseball, let's use P equals mv. The momentum of the electron, it has mass, so let's use P equals mv. You're asked to find the momentum of a proton, then let's use P equals mv because it has mass. But if you're asked to find the momentum of a photon, a particle without mass, then let's make sure we use one of those equations in the top right-hand corner of your data sheet. Not P equals mv, but P is equal to E over c or P is equal to H over lambda. Good? Let's take a look at an example that's not in your textbook. It says, calculate the energy and the momentum of a photon whose wavelength is 600 nanometers. The energy is old for us, right? We've done that for a week now. The energy is simply E is equal to hc over lambda. Easy enough. Let's do this in joules. 6.63 times 10 to the minus 34 joules seconds times c, 3 times 10 to the 8, divided by lambda. 600 times 10 to the minus 9. I'm not going to forget to convert that because I've circled the nanometers there. Somebody during the practice test this morning came up and was asking me a couple questions, and I answered them because it's just a practice test. It didn't count for anything. On a couple of situations, he forgot to convert units, and I just about lost it. Why did he forget to convert units? Because when he was reading the question, he didn't circle nanometers or millimeters or whatever. Okay, circle that. Draw attention to it so that we don't forget. What do we get for energy there, by the way, when we do that calculation in meters? 3.315 times 10 to the minus 19 joules, which we're actually going to round to 3.32 times 10 to the minus 19 joules. Now, if we want to find the momentum of that photon, we've got a couple of options. On our data sheet, we see E is equal to P times C, or P is equal to E over C. We also see P is equal to H over lambda. Now that we have the energy, we can divide that by the speed of light to get momentum. Or we can go back to our original data and just say H over lambda, 6.63 times 10 to the minus 34. By the way, you're always using the 6.63 value in these questions, always. Never the 4.14 value. When we do the math on that one, we end up getting 1.11 times 10 to the minus 27. And as odd as this seems, our units are going to be kilograms meters per second. We've got a particle with no mass, but its momentum is measured in kilograms meters per second. So either equation for momentum will get you that same answer, whichever one you prefer. Let's take a quick look at these three questions on 723, please. Briefly, let's talk about question number 3 here, then we'll do question number 2 as requested. 2 photons here, 10 nanometer, 11 nanometer photon. We want to find out how much energy the electron gains. Notice that the wavelength of the photon has gone up. We've gone from 10 nanometers in question number 3 to 11 nanometers in question number 3. Didn't we say the energy is going to go down? The second less energetic photon? We did. The energy goes down. But since E is equal to hc over lambda, if energy goes down, then wavelength goes up. So this is predictable. We should expect to see a higher wavelength because we have a lower energy and therefore a lower frequency. But the only thing that I know is to find the energy of the photons, not the energy of the electron. So here's what we're going to do. For question number 3, we're going to calculate the energy of the 10 nanometer photon. Let's get the energy of the 11 nanometer photon using the same equation. Let's get the two of those and let's subtract them. When we do that, understand that we've just solved for the energy of the energy change of the photon, not of the electron. But if the photon loses this much energy, then how much energy did the electron gain? Same, right? So if we solve for the energy lost by the photon, it will be the same value. It will be 1.8 times 10 to the minus 18, the same as the energy gained by the electron. If there's only two things in the mix here, photon and the electron, one loses energy, the other's got to gain the same amount of energy. All right, let's take a look at number 2 here as well. What's the momentum of an X-ray with a wavelength of 10 nanometers? We have two equations that are on our data sheet for momentum of photons. E is equal to P times C, and we have P is equal to H over lambda. So we're going to say 6.63 times 10 to the minus 34. Remember, we always use that 6.63 value for Planck's constant when we're dealing with this photon momentum stuff. Divide that by the wavelength, which is 10 times 10 to the minus 9. And we should end up getting 6.63 or 6.6 times 10 to the minus, I guess, 26. Is that right? Is that right, the answer on the sheet there? Is that okay, Dylan? Okay, so you wrote it down like this, though? Let's pull it up on the calculator and see what happens here, okay? Okay, let's say 6.63 times 10 to the minus 34. Okay. Divided by 10 times 10 to the minus 9. Oh, that gives me way different. Oh, yeah, 10 to the minus 34 it should be. 6.63 times 10 to the minus 34. 6.63, let's try that again, one last time. 6.63 times 10 to the minus 34 divided by 10 times 10 to the minus, this isn't working very well. Not funny, you guys. Don't make fun of me because I have trouble hitting buttons here. 10 times 10 to the minus 9. There we go, 6.6 times 10 to the minus 26 is right. Good? Oh, here's a question that doesn't even look familiar at all. It's because we don't have an equation that describes that. Let's go back here to the fun equation. If we've learned E is equal to P times C, which is on your data sheet, and we've learned P is equal to H over lambda, which is on your data sheet, well, now we're going to learn an equation that describes the change in wavelength. Delta anything is something final minus something initial. Delta lambda is lambda final minus lambda initial. That's easy. It's the second part of the equation that's kind of challenging. H over MC times 1 minus cosine theta. H stands for Planck's constant. 6.63 times 10 to the minus 34 joules seconds. Once again, we're always going to use that value for these photon momentum problems. M, well, that's a mass, right? Photons don't have any mass, so we must be talking about the mass of the electron. 9.11 times 10 to the minus 31 kilograms. C is the speed of light. 3.00 times 10 to the 8 meters per second. Those three variables are always going to be the same in this equation. The only thing that actually changes in this equation is theta. Theta stands for an angle, obviously, but specifically, it's the scattering angle of the photon. The X-ray strikes a piece of metal and electrons ejected. A second less energetic X-ray is also emitted at an angle. Theta is the angle between the original photon and the new photon. If you're ever given a question where you have the angle of the electron, ignore it. I doubt you'll ever be given a question like that, but if you are, ignore it. We don't want the angle of the electron, we want the angle of the photon. Now we can solve that question that looked a little bit foreign to us just a minute ago. Here we have an X-ray photon of wavelength 0.0500 nanometers. That's the original wavelength. That's what it starts out as. Scattering at an angle of 30 degrees. We call that theta. We're looking for we're looking for lambda f, the final wavelength of the photon. Okay, what it becomes. We should expect the value of that wavelength to be higher. The energy goes down, the frequency goes down, the wavelength should go up. So we should expect to get a value for lambda f that's bigger than lambda I. Let's see what happens here. Delta lambda is equal to lambda f minus lambda I, and that's equal to h over mc times 1 minus cosine theta. Lambda f, therefore, becomes h over mc times 1 minus cosine theta plus lambda I. All we're doing here is taking lambda I over by adding. Now the equation looks even uglier. It's really not that bad, though, when you start putting numbers in and going to actually solve it. We're solving for lambda f, yes. H is 6.63. Always going to use the 6.63 value in these problems. Let's put this into our calculator and make sure that you can do this yourself as well, okay? We've got 6.63 times 10 to the minus 34. We divide that by, let's use some brackets on the bottom here, 9.11 times 10 to the minus 31 times 3 times 10 to the 8. Let's end those brackets. Okay, that's the number, the coefficient that we get out in front. Let's multiply that by 1 minus cosine theta. Times it by, again, use some brackets, 1 minus cosine 30 degrees. Make sure you're in degree mode. End the brackets, both sets of them. Press equals. And then let's add that to the initial wavelength there, which is 0.05 times 10 to the minus 9 meters. When we do that, we get 5.03 times 10 to the negative 11. This, if we converted it to meters, would be 5.00 times 10 to the minus 11 meters. We get 5.03 times 10 to the minus 11 meters. Did we get a bigger value? Yes. Should we have? Yes. Bigger value of wavelength means smaller value of energy, and we know that that second photon has to be less energetic. Done. We got one practice problem on this stuff for you that I'd like you to work, and then we'll do one more example, and then we're done for the day. Try this one, please. Yep. Lambda f.
Yeah,
Lambda f, lambda I. Well, lambda, its equation is delta lambda. You go to h over mc minus cosine theta. The delta lambda is lambda f minus lambda I. So far, so good?
mm-hmm.
If we want to take that over, if we want to find lambda f, we take that over by adding, right, because it's negative lambda I.
But I'm saying is how do you know like
Oh, the value that you're given?
how do you know?
Oh, okay. 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 If it says an X-ray of wavelength 0.01 nanometers scatters, then what you start with is scattering. Okay. If we have a group of people, standing in front of the school on a Friday night, and the police come and they scatter, well, the group of people is what we started with. Okay. Yes. Okay. So we have an X-ray here that has a certain wavelength. It scatters. So what scatters is what we start with. That's going to be our initial. Does that make sense? No problems, Christine? Got it. You guys are good at this question? Any issues? If you were here to do it? Good? Can we go over it? Yeah. Yeah, for sure. Okay, let's take a look here then. An X-ray of wavelength 0.010 nanometer scatters at 90 degrees from an electron. What's the wavelength of the scattered photon? Similar to the question that we just did a minute ago. Delta lambda is equal to lambda f minus lambda I equals h over mc times 1 minus cosine theta. Let's solve for lambda f. Take the lambda I over by adding. So it becomes h over mc times 1 minus cosine theta plus lambda I. Does that make sense, what we've done there? All right, h over mc is always the same value. We multiply that whole coefficient by 1 minus cosine 90 degrees this time, plus lambda I is 0.010 times 10 to the minus 9. We should expect to see a bigger wavelength because we have a decrease in energy. So I don't know what it's going to be, but it should be a bigger value. We multiply this, divide it by 9.11 times 10 to the minus 31 times 3 times 10 to the 8. And what did we get the last time we did that? Don't have it there. What is that coefficient there? Anybody have that? 6.63 over 9.11 times 3? .44259? 10 to the negative 12? Now, cos 90 is 0. 1 minus 0 is 1. So 2.4259 times 1 is 2.4259. Minus, or added, I should say, 0.010 times 10 to the minus 9. We add those two together, and we should get 1.2, I believe, times 10 to the minus 11, which is 0.012 nanometers. Okay? Let's try one more example here. Hopefully we have time for this. What's the maximum change in wavelength that an X-ray photon can undergo by Compton scattering with an electron? Does the initial wavelength matter in this example? No, it doesn't. I'll tell you that right now. The initial wavelength doesn't matter. What's the maximum change in wavelength that we can have? Well, we know that delta lambda is equal to h over mc times 1 minus cosine theta. Now, h is 6.63. It's not going to change no matter what. M is not going to change. It's 9.11 times 10 to the minus 31. And c isn't going to change. It's the speed of light. The only thing that we can change here to get a bigger or smaller value of delta lambda is theta. That's the only thing that we can change. So what do we got to make delta theta in order to make delta lambda the biggest possible number? Let's try a few different possibilities. Okay, let's make theta equal to 0 degrees. Let's make theta equal to 90 degrees. Let's make theta equal to 180 degrees. The logical values. And if we do that, then cos theta becomes what? Cos 0 is 1, cos 90 is 0, and cos 180 is not 1, negative 1. All right. Well, if cos theta is 1, 0, negative 1, then 1 minus cos theta is what? 1 minus 1 is 0. 1 minus 0 is 1. 1 minus minus 1 is 2. This is the angle that maximizes the value of delta lambda. Do you see why? That's the value that gives us 1 minus cos theta is equal to 2. And that's the biggest possible number that we can get inside those brackets is 2. We get that from having an angle of 180. So the equation becomes h over mc, the same values as they always are, times 1 minus cosine 180, or 1 minus negative 1. Basically, it becomes twice the value of h over m times c. Get it? Okay, you can plug those numbers into your calculator and get a number for it. Whatever it works out to be, it's always going to be that number, regardless of whether we start off with 0.01 nanometers or 0.05 nanometers. We always have the same value. All right, that's it for today then.